Now, we've talked about the equilibrium constant. Generally, there's two types. There's Kc, which describes the relative concentration of reactants and products. This is described in molarity, molar, or moles per liter. So, discussing this reaction here, you would put the products over the reactants, and you would still use the coefficients as the exponents, and you would use brackets to describe the molarities of these compounds. But you also can sometimes use Kp. This describes the partial pressures of gases in atmospheres. So the pressure of the products over the reactants, where our pressures here are talking about just the partial pressures of the specific compounds. And of course, you can still see that we're using coefficients. Now, you can interconvert between Kp and Kc. Kp is equal to Kc times, parentheses, RT, parentheses, to the delta N. Now, R is the gas constant, and being that we're using atmospheres in our Kp, the gas constant is going to be 0.0821 liters times atmospheres over moles Kelvin, instead of 8.31 liters times kilopascals over moles Kelvin. And our temperature is going to be in Kelvin. Now, our delta N, this is the change in moles, actually the number of moles of gas, just looking at the balanced chemical equation. So, it's the number of moles of gaseous product minus the number of moles of gaseous reactant. So, you can see in this case, delta N is equal to the number of moles of gaseous product. Now, in this balanced chemical equation, there's 1 mole of this gaseous product, and then we subtract out these 2 moles of this gaseous reactant. Of course, you couldn't apply the number of solid or liquid particles within this calculation. Now, oftentimes, the change in the number of gaseous particles in the reaction will be equal to 0, and hence Kp will be equal to Kc. Now, I want to mention that these Kp and Kc, these constants, they do not have units. Although they might have units, we don't show them. It's just not typical. All right, kind of moving on to some smaller topics. We have, let's say, discussing acetic acid reacting within a solution of water. It dissociates and leaves you acetate and hydronium. Now, another way of writing this, which you'll get to in the acid-base chapter, is instead of writing hydronium, you replace that with just an individual proton, and then you do not account for water. And so these two ways of writing this reaction, they are equivalent. And we're able to still keep the same equilibrium constant whether we're discussing either of these ways of writing the reaction, because we ultimately do not include solvents within the equilibrium constant expression. Now, we might take a look at this top reaction and say Kc prime is equal to the concentrations of the products over the reactions. But given that water here is a solvent, and it's about 52 molar, highly concentrated, pretty much no matter how much of this reactant actually reacts, that water is not going to be consumed to a significant extent. It is not going to be changing concentration. And so, considering that, we can include this within this constant expression and say that the equilibrium constant then for this overall reaction is equal to the concentration of our solvent water times Kc prime here. So ultimately what we do is we just say that the equilibrium expression, it does not include water if water is a solvent. And occasionally might include other solvents like methanol or ethanol. Now, you'll note that by following this kind of rule, we see that the equilibrium expressions, they will end up having the same values regardless of whether you use this top or this bottom way of describing the reaction. You see that hydronium concentration is really the same as proton concentration, so it all works out. Now, we can also talk about, whereas that was homogeneous equilibria, talking about within a solution, we also can talk about heterogeneous equilibria, in which we have different states of matter. Oftentimes, we might have some pure solid within the reaction mixture, or some pure liquid. Now, we do not include pure solids within the equilibrium expression. One reason might be that it's really difficult to describe the molarity of a solid. And that molarity of the solid is only that certain molarity within that solid and not within the overall mixture. But another issue is that those molarities of your solids don't change. You might lose some of that solid on the exterior, but overall the molarity doesn't change. So, being that its concentration doesn't change, we end up getting rid of solids and then also pure liquids from equilibrium expressions. So, for this reaction, where we have two solids, we do not include those in the equilibrium expression. However, we do include gases. Generally, what we'll do is we'll include gases within equilibrium expressions, and we'll include aqueous compounds, not pure solids or pure liquids. Thanks for watching, guys.